Now that we have finished discussing the relative dating part of our lecture, let's go ahead and discuss absolute dating. And looking at this image would already give you an idea of the advantages of absolute dating. So far when we are looking at rock strata, we have been describing them in terms of younger, youngest, older, oldest. So that's relative dating. But when it comes to absolute dating, you just need the original material. So the original material themselves and analyzing the material within could already give you an estimate of when did the rock layer form. So for example, here we have 140 with a margin of error, of course. So 140, give or take 10 million years. So between 130 to 150 million years ago, this rock layer was formed. So same goes for this rock layer. So this was formed 120 with a margin error of 5 million years ago. So between 115 to 125 million years ago, this layer was formed. And that's already very informative in comparison to relative dating. So absolute dating uses radioactive materials. That's why it's also called radiometric dating. So in the absolute dating method, we should be using radioactive isotopes. So as you know, isotopes are just versions of it's the same atoms, but they have like a different version of the atom itself because they would have a different mass number. But because they have a different mass number, it leads them to becoming radioactive. So due to the extra subatomic particle in the isotope, the atom spontaneously breaks apart, which produces a more stable daughter product. So every radioactive isotope will decay and turn into a stable daughter product. Okay, so the transformation of parent isotope to stable product varies from element to element and is often measured in terms of half-lives. Okay, so take a look at this chart. Okay, so it's already showing you the radioactive parent, the radioactive isotope, can decay or will decay into a stable daughter, and we already know the scientists have already identified the half-life of each material. So for example, rubidium 87 will become a more stable strontium 87, but that would take a half-life of 48.8 billion years. But what is a half-life? So as it states here, the half-life is the length of time that will transform half of the parent isotope to its daughter product. That's why half-life. Okay, so let's give a more exact example. Okay, so for example, I have that was rubidium. Okay, so I have 100 rubidium here. So rubidium is a radioactive material. Okay, rubidium 87 is a radioactive material and it will naturally decay into strontium 87. Okay, so half-life is when half of the material will turn into the daughter product. Okay, so for example, here you have rubidium. For example, I have 100 atoms of rubidium 87. So the time that it required for it to turn, like half of the rubidium 87 to turn into strontium 87 is called half-life. Okay, so that is how long? 48.8 billion years ago. So for the case of rubidium, our half-life is 48.8 billion years. So that means it would take 48.8 billion years to convert half of this rubidium 87 to decay into strontium 87. So very useful because you can, if you were able to look at a certain material, okay, and identify the ratio of rubidium-87 versus the strontium-87, then you can have an estimate of how much time it has already progressed since the original material towards the um, here the daughter material. So this is 48.8 billion years. Okay. You can also look at this in terms of ratio. So for example, here we have 1 is to 0. You have 1 parent isotope and you have 0 daughter. But by the half-life, you have 1 is to 1 because they're equal now. 50%, 50%. So you have half of it is rubidium-87, half is strontium-87. How about in another half-life? So in another half-life, so let's put a 1/2 here just to like identify that it's a half-life. So in another half-life, okay, so whatever is left here, so we had 150, so whatever was left here would add like half again. So from being 50 strontium 87, it will now be 75 in total. We have 50 strontium 50 strontium 87 here. Now we have 75 strontium 87. So you have a 25 versus 75. So that would um, change the ratio. So you have here a different ratio. There. So that's our half-life.